Hello everyone. Well, I welcome you all once again for this wonderful session on machine learning. I tried to make you explain what is dimensionality reduction. However, I couldn't, but you already know that what is the intuition behind dimensionality reduction in unsupervised learning. Well, in a short overview, what do you mean by DR is DR will give you DR means dimensionality reduction. Well, this reduction in dimension basically gives you an intuition that while working with higher dimensions, our system is going to be more complex. You understand this? Your system is going to be more complex, and the idea to resolve this, we can have a lower dimension. Okay, we need to convert our data set in a way that it becomes a lower dimension, and then we can work it out. Okay, so this is the main intuition behind dimensionality reduction. We'll discuss about dimensionality reduction in our later sessions, but however this session basically prescribed to principal component analysis, which is you can say the subtopic of DR. Okay, so let's get started with principal component analysis, which we tried early morning to discuss. However, with some technical issues I couldn't, but this session I'm gonna make you explain what is PCA. Okay, so the principal component analysis, shortly abbreviated as PCA. Okay, well, this PCA, the main idea or the main motivation behind PCA is also the reduction in dimension, what we had discussed in DR. Okay, so the thing is, if I have a data set, let's say, you already know that to work around with dataset and generally with machine learning, you definitely need a larger amount of dataset. So let's say I have a dataset of around let's say this is a 2 TB of data. That means they have definitely larger number of rows and larger number of columns, right? So it is, let's say this data is n cross n dimension data. Okay, so the all features, so that my x, let me just move this, my x belongs to the n dimensional vector space. Okay, so your data set is in a larger feature space, so I cannot work around with this data set. Why? Because if you are having this much of data set, this huge amount of data set, then basically to represent this 2 dB of data, I need n dimension space. Okay, I need to represent my data set in a n dimension space. Well, I don't think I can work around with n dimension space, because this will become my system more complex and more tidy to understand you. Okay, so what I can do is I need to reduce this I need to reduce this n dimension space to some k dimension. Okay, I need to reduce this n dimension to k dimensions. So in general, let's say this is a 3 dimension space, so I need to reduce it to 2 dimension. This is my intuition. And why I basically doing this is because if I have this huge data set, this will create a problem such as it will give me more number of relationship. You understand this? Because I have a large data set, a huge number of data, like n rows and n columns. Because of that reason, I will get more number of relationship here. And when you get more number of relationship, that means more number of variables. Okay, so more number of relation, that means you are having more number of variables. And when you are working with more number of variables, that means your model is going to be, let me just change my color to some other so that I can show you that. So if you are working with more number of relationship, that means you are likely to proning your system with an overfit model. Okay, you will likely to get your overfit model here. Why? Because you already know that an overfit model has a property called high variance. That means if I have a data set looks like this, then an overfit model will try to try to collect all these data points, and it will create a graph looks like this. Okay, this is an overfit model, and the problem is here is the high variance. Okay, this is the reason I will get this kind of graph. Okay, and this is basically not a good idea to have an overfit model. This is wrongly interpreted over here. So this huge number of rows and columns will create a problem called as more number of relationship between variables. And when you're having so many variables, like in this model, you can see there are so many variables x x x x, then you need to cover all these data points and need to create a graph looks like this. And this is an overfit model, and I don't need this overfit model. This is not a good idea to have an overfit model here. I really don't need in my machine learning that I get this overfit model. I need to reduce this overfit model to a good model, and how I can do that is to, with the help of two mechanisms, I can do this. One mechanism is feature elimination. This is one way you can reduce or you can work around with the overfit model. One is feature elimination, or another one is feature extraction. Okay, both these things can deal with an overfit model. Are you getting it? I hope you are getting it. Okay, I don't need this overfit model. To deal with this overfit model, I need to reduce my dimension from n dimension to k dimension. And how can I do that? With the help of these two mechanisms, feature elimination and feature extraction. Now the thing is, I need to understand what basically these two methods are doing here. Well, a feature extraction, if I make you explain what is feature extractions, let's say I have 10 independent variable. Okay, so I have a 10 independent variable, and when I say independent variable, by means of independent variable, it is nothing but your y component. So if I have a equation y equals to mx plus c, then my y is I'm so sorry, this independent variable is x. I'm so sorry for this. Y, where in this equation y is going to be your dependent variable. So this is going to be your dependent variable, and here in the case of this x is going to be your independent variable. And why is that so? Is because whatever the value you are giving over here, your y is going to change, right? So that's why this y is completely dependent on this x component. However, the x component is not depending to anyone. So this 10 independent variable here is going to it's going to give you this 10 new independent variable is going to give you 10 new independent variable. Okay, so this 10 new independent you will get is the combination of new and old. So this is a combination, it's going to be a combination, it is a combination of the old variable, and let me just draw a line, and a new variable. So okay, so this is basically well, you will get a you have 10 independent variable, and you will get 10 new independent variable with the help of these 10 units. So if I have, let's say, by means of feature extraction, what I'm saying is, so let me just draw over here. So if I have x1, x2 and x3 as a value, like let me draw it out like 0.58, and let me have 1.8, and let me have 2. Let's say, oh, I'm so sorry, let me have just 1.5. okay, so what I'm gonna do is, I have x1, x2, x3, and then I can have, so this is my independent variable. Okay, so this is my just independent variable, and I, with the help of, let me just separate it out. So with the help of this independent variable, I will get new independent variable over here. So 0.5 could be like, let me just say 0.6, could be like this is 2, and it could be like this is 1.5 itself. So I will get new variables such as z1, z2 and z3. It is in the data set itself. Okay, no worry, you don't need to create these numbers, but you are, So in the data set, just like for an example, your 0.58 is here, your 1.8 is here, and 1.5 is here. So in a very near so this is my one data point, this is two data point, this is third data point. But in the, let me just change the color so that you can understand. And these, the new data points, so if this is my x1, x2, and this is x3, and then I can say that very near to this 1.5 I have this z3 here, okay, and very near to this is z2, and very near to this I have z1. So you are taking those near data points which are likely to be x1, x2, and x3. So with the help of this 10 new independent variable, you are getting 10 new independent variable, and it is a combination of old and new. Okay, so this is the feature extraction. I hope you are getting it in the data set. So this is feature extraction. And when I say feature elimination is easy to understand. It is nothing but you are dropping some variables. So in feature, I'm just writing the abbreviated form, feature elimination, so EL, it says dropping some variable from data set. Okay, feature dropping some variable from data set. By means of dropping, you can drop some variable who is having high coefficient value. So you are dropping those variables so who's having high coefficient value. Okay, so you are dropping these high coefficient values, such as if my x1 is having a range of 1000, I'm going to drop it. If my x2 is having a range of 2000, I'm going to drop it. However, my x3, x4, x5, they all are in the same range. Let's say it is in the 10, this is 15, this is 16. I'm going to be okay with this. I'm not going to drop it. However, these high range are going to be dropped out. So okay, so this is feature elimination. I hope you're getting it. Why? I mean, in feature elimination, we are definitely losing some information from the data set, but it is necessary part. Okay, otherwise you are not reducing your dimension from n dimension to k dimension. Okay, so this is the problem formulation, you can say, of the PCA, where we are reducing our n dimension space to k dimension space. And how can you do that? With the help of feature elimination or feature extraction. Now, when you're dealing with PCA, PCA is basically come and exist. It come and exist in feature elimination. So your principal component analysis, your principal component, let me just write it PCA, it is a feature elimination. It is a feature extraction mechanism. Okay, please remember this, that your PCA come and exist in feature extraction, where with the help of 10 independent variable you are creating 10 new independent variable. Okay, I hope you are getting it. So so let's say I have a graph in PCA. So let's say this is the graph. What I'm gonna do is I have a graph, and I definitely need some other color to represent my data points here. So let me just take pink color over here. So let's say I have a point here, a point here, point here, and let's say I have a point here and a point here. Okay, so what this PCA is going to do is it will create a feature space here. It will draw a line. Let me just change the color. I need to change the color to show you the visualization of the this thing. Okay, so let's say this is the, I can't draw it. Okay, so this is the line. This is the line of feature space. So what this PCA is going to do, that I'm right now I'm in the 2-dimension space. So this is my x2 and this is my x1. What I'm gonna do is I will change from 2D to 1D. Okay, so to do that I need to project these data point, these x data point, into the to this line. Okay, this perpendicular line I need to project it. And how can I do that? Is with the help of projection technology or projection mechanisms. So I perpendicularly draw a line and I will project my data point. Okay, again I draw a line and I project it here. Again draw a line and I will project it. draw a line and I project it, and this is already in. Okay, so this is the projection that we did, right? Now by means of projection, I hope you understand now the projection meaning. Like if I have a data set looks like this, I'm just giving an idea from the data set that what exactly happening in the data set. So if I have x1, x2, x3 and so on, let me have also x4, x5 and so on. So basically what is happening over here in the with the help of this projection, so if I have x1 as a value called 0.5 and then let's say 0.6, this is like 1.8, 1.7, let me have this is 2.3 at 2.9, this is 1.9, this is 1.8 and so on. So okay, so what I'm gonna do over here by means of projection, so if I have a value as 1.8 in the x2, so when I represent in the graph, okay, when I represent this x2, x1, x3, x4, x5, what is happening is this is 1.8, let's say, then my 1.9 is going to come over here and 1.8 is going to become over here. So by means, so let's say this is the 1.8 of x2, then this is the 1.8 of x4. So these 2 points are very near to each other. So x2 is already here, so let's say this is the x2, so this projected value is nothing but x4. Okay, so I'm projecting another value from the data set, and that is going to be that is going to be my new independent variable. Okay, and that is nothing but the projection. Okay, so here x, when I say x, is nothing but your actual data, and when I say this round shift x, it is nothing but projection. Okay, projection of actual data. I hope now you are getting the PCA formulation. So we are projecting our actual data to some nearby nearby data point, and we are reducing the this 2 dimension into 1 dimension. And how we are reducing, I'm going to show you, and you can easily see that initially I was working with 2 dimension x2 and x1. Now I have a line here, and on this line I have all the projected values. So if I have this x1 here, x2 here, and this x3 here, x4 here, and x5 here, now you can see I have all the point here in the one line only. So this is my x1, x2, x3, x4 and x5. I already converted it. Can you see this? This is x4 and x5. Okay, so from the 2D I'm converting or projecting this from 2 dimension to 1 dimension here. Okay, this is what I did in the PCA. So PCA is going to, I'm going to write it over a statement. PCA is going to find a lower dimension space such as 1D, okay, and wish to project the data, that means finding new variable by means of projecting, that means it is finding new variable from the data set, so that it is also very important, so that the sum of squares, this is square, all right, let me write it down. The sum of squares of these distance, get minimized. Okay, distance gets minimized. This is also very important, this last line. Okay, so I'm reducing, definitely I'm reducing from 2 dimension to 1 dimension, but also take care that you are working with sum of squares of these distance get minimized. I also need this. Okay, so if I am projecting something from here to here, then I need that this distance, sum of squares of these 2 data points, is going to be minimized. Okay, I need that data point which can minimize the distance between these 2 data points. Okay, my actual data point and the projected data point has to be minimized. The distance is going to be minimized. Okay, so this is PCA. And one more important thing over here, that while working with this projection, please keep that in mind, that I had shown you that this is the um, line where I am projecting. So these are the point, and this is the line, this is projected, and my x value is here. Oh, I'm so sorry, I should not this yeah, I shouldn't do that circle, because circle represent the projection. Okay, so this is the best projection, this is the best projection line, this is the best projection. However, there is one more line that you can draw over here, but then it will, it is not going to be the best projection. So how can you project on this line? Well, you need a perpendicular line and you will project here. Okay, you need a perpendicular line and you will project here. You need another perpendicular line and you will project here. Now you can see the distance between the actual data point and the projected data point is very high. Okay, these distances are very large. So this is basically the worst projections. Don't use it. You need to find a vector space of this projection feature, of this projection, that what is going to be the best and what is going to be the worst projection. If you are taking this worst projection, then the sum of squares of this distance is not going to be minimized. They are going to be very high, and your PCA is not going to work. Your PCA will give you a higher dimension always. Okay, it is not going to be lower down. Okay, so keep that in mind, that you need to be, whenever you are projecting, you need those independent variable, new independent variable, which are very near to each other. Okay, so this is what we want in the PCA. Now I'll give you the PCA algorithm, that what exactly happening in the PCA. I had taken these notes from the N2NG course. I'm really thankful for that. If you don't understand my lecture, you can go and refer also those videos. They are pretty good in content. However, I had taken the source and the algorithm from that video. Okay, so I'm thankful for the N2NG course. Okay, so now PCA algorithm. What will happen in PCA is, so in the PCA algorithm, let's say I have a training set. My training set for the unsupervised data set, it looks like x1, x2. Okay, these are the indexes, and let's say this is the xm. Okay, so this is my training data set. And keep that in mind, that this is a very important point here. Before applying PCA algorithm, you need to apply something called as feature scaling, and we had precisely seen this mechanism in our third or fourth chapter, where feature scaling says that you don't directly use the data point, but you use something called as scaling, okay, before using that data point. So what is the feature scaling? So by means of feature scaling, what you can do is, if you are having x of I, then you can create a scaling factor such as this, x minus u of j. And if this is the jth jth feature, then I can use something like this. Okay, so this is the scaled feature now. Okay, this is the scaled feature. So by means of scaling, it means nothing but if it is in the range of 100, then this scaling will give you in the value of 0.5 to of 1. Okay, so the value is going to be like in between 0 to 1. Okay, any value. So you are scaling your feature from xj to xj minus uj. This is the very important feature, and more precisely, you can put your scaling factor as u of j belongs to, you can take any scaling factor such as mean max normalization, or the range factor, or likewise. Okay, so this is averaging, you are doing averaging from j to 1 to m, or actually this is I, and you're scaling all those vectors. Okay, so you are scaling all your feature which is there inside this training set, and you're converting that into the mu j, xj minus uj. Okay, so this is the first step before starting with the PCA algorithm, right? Now in the PCA, what so after these two steps, you will apply your PCA intuition. So what you will write here? So you will write reduce. After that 2 point, you will write, this is the third point, reduce data from n dimension. You can see clearly, you can see here we are reducing the n dimension to k dimension. This is pretty much important point here. This is the problem formulation of, or you can say the intuition behind the PCA. So you are reducing the data from n dimension to k dimensions. So for that, what you can do here, you need to compute something called as covariance matrix. Okay, so you will compute covariance matrix. Okay, and I will not give you the mathematics behind this covariance matrix. You can find any resource over the internet to see the maths behind this covariance matrix. Okay, and we can represent this covariance matrix with the help of this sigma sign, and I will not draw this sigma sign like this because it is also the sign for summation, so I will simply write sigma. Okay, I will write sigma here. So the sigma, it looks like, or your covariance matrix is going to be like this: 1 by m summation of I equals to 1 to n, and your xi and your xi is going to be here transposed. Okay, this is going to be like this. Okay, so you can see your sigma, your covariance matrix looks like this. Okay, your all training set is multiplied, or it is going to be multiplied with the transpose of that the training set itself. Okay, all the variables you are one is the xi is going to be multiplied with xi of transpose itself. Okay, so you are multiplying two matrices with one of the same, but the other matrices is going to be in the transposed version. Okay, so you are going to use this sigma, and to find this sigma, what you can do is, if you want to find the sigma, then you need to find something called as eigenvectors. Okay, so compute eigenvectors. Don't go for the mathematics behind this, all these things, but these are the steps for the algorithm. Just keep a like on that and you will get the idea. So compute eigenvectors of the matrix, I mean to say the sigma. Okay, covariance matrix. Okay, so compute the eigenvector for that. So what you're doing here, to find the eigenvector of this covariance matrix, you can use one thing you can use is, you can use something called as EIG function. Okay, EIG of sigma will give you the eigenvector for this sigma, or either you can use SVD. The SVD is I need to write it over here. This is SVD of sigma, which also both will give you the eigenvectors for sigma. Okay, eigenvector for sigma, both will give you SVD. Here it is nothing but singular value decomposition. Okay, singular value decomposition. So both these function EIG and SVD will give you the eigenvectors. So I can represent, or I can put it over here in this way. Let me just take the other color. So I will write here, what you will get from the, I'll take the eigenvectors from the SVD function, and the SVD function will give me three factors over here, and these three factors are nothing but matrices. Here three matrices, these two matrices are the orthogonal matrix. These are orthogonal matrix, and this V here, oh I'm so sorry, this U and V. Okay, this U and V are the orthogonal matrix. However, this S is going to be the diagonal matrix. Okay, this is diagonal matrix. So your SVD function, which gives you the eigenvector, it in the form of three matrices, which is U, S and V, where U and V are orthogonal matrix, whereas the S is the diagonal matrix. Okay, so we are pretty much focusing on this U matrix. Okay, so I'm interested in this u factor or the u matrix. Okay, I'm pretty much interested in u. So we will write it over here. We need u matrix more precisely, more precisely over here. Okay, and your u matrix is, I will write it over, your u matrix is n cross n matrix. Remember, I need to convert this n dimension into k dimension space. This is the problem formulation of PCA. So my mu matrix is n cross n matrix. Okay, so it represent it looks like this. So mu1 and then mu2 and so on to mu k. Okay, this is how your n cross n matrix going to be look like. Okay, so this is, so your mu belongs to R n dimension space. It represents in the n cross n matrix. That means it is in the n dimension space. Okay, so what I'm gonna do is, if I want to do the PCA, then I want to reduce the, what we want here is, this is n cross n matrix, and again we want here, we want to reduce a dimension, we want to reduce dimension from n to k. So how can I do that? This is n cross n, I will take k dimension from this n. Okay, so I need this k dimension from this n dimensions. Okay, so what I'm gonna do is, I will take the first k column from this n dimension. So I'll grab this box, and this box represent my first k column. Okay, first k column. Okay, I will take the oh, I'm so sorry, this is not k, this is m actually. Okay, this is m. So my training set, if you remember, my training set x1 is going to be xm. This is my training set, so that's why I have the eigenvectors as mu1 mu2 to till mu m, and I'm taking the first k column because I need to reduce this this complete data set from this um, from n dimension to k dimension. So that's why I'm taking the first k columns from the n cross n dimension. Okay, so what I'm gonna do here is, I will take, this is my mu. Initially it looks like this, mu1, this is mu2 and till mu m. So I'm taking only k columns from here. Taking k columns, and by the way, this is n cross n. So now your so I'm representing this mu now in terms of z, and your z is going to be mu1 mu2 till mu k. Okay, this is my mu reduce. Okay, so this is my mu, and now this is mu reduce, and I am representing this mu reduce with this letter z. Okay, and your z belongs to R n cross k dimension. So this is n cross k matrix. Okay, remember that this is my n cross k matrix, which was earlier n cross n matrix. Now it is n cross k matrix. Okay, next thing is, what I'm gonna do is, I'm going to transpose this. So my complete mu reduce, which looks like, earlier it looks like this. Okay, it looks like this. I'm so sorry, I'm slow on this, and this is n cross k earlier. Now I'm going to reduce it, I'm going to transpose it, sorry. So mu reduce is going to be now transpose it, and it is going to be multiplied with x. Okay, this is my x feature space, this is my training set, and this is n cross 1 dimension. So this is my so it is earlier n cross k, now it is going to be k cross n matrix. Okay, earlier it was n cross k, my mu reduced. Now I transpose it. Because of this transposition, I have k cross n matrix now, and this is already the feature space n cross n. So it looks like this. Let me just normalize this and some other color. So it looks like this. So mu1, mu2, and so on mu k. Okay, and I already have the x. So this is going to be k cross n, which is going to be multiplied with n cross 1, and this complete thing, when it is going to be multiplied, you will get k cross 1. So if you remember earlier, so you can see here, this is k cross 1. Earlier my mu was n cross n. Now my mu is basically k cross 1. So you can see here, I'm reducing my n dimension into the k dimension space. Okay, this is done with the help of PCA, and this is what we see in this complete topic. We are taking or we are reducing the n dimension space into from n dimension space to the k dimension space. This is what exactly we want in the PCA, the dimensionality reduction algorithm. Okay, so this is what we see. The intuition behind the PCA is to reduce it, and we precisely had done this. So I can say that my x that was belongs to R n, now it belongs to z. I'm representing this, I'm projecting this. Okay, I'm doing nothing but I'm projecting this x into z, and now it belongs to R of k. And this is this precisely the thing that we seen in PCA. Okay, so I hope you are getting it. This is principal component analysis, and if you have any doubt, you can ask me in the comment section whenever you are I mean available. Okay, I'll shortly write the algorithm in few steps, and I already told you that I had taken this complete algorithm from the NG course, so I'm thankful to that. So the pseudo code for this, so the pseudo code for PCA algorithm, it looks like this. So your sigma is important here. Sigma is the only thing that we are, the covariance matrix that we are dealing with. So okay, so this is the pseudo code, and you can see the sigma function, and which this is the x, I mean the training set, and it is multiplied with the training set transpose of that. Okay, and we can get this sigma with the help of this SVD function, which is singular value decomposition, and the output of this SVD sigma, you will get three matrices U, S, and V, which are nothing but eigenvectors. So we are very important, this U matrix, which is very important, and we are interested in this U vector, which is n cross n matrix, and we want to reduce this n cross n into, so I want to reduce this n cross n into k cross 1. This is my thing. Okay, so the you reduce, you will get the k column. You will grab the k column from this matrix n cross n. You will get the first k column from n cross n matrix, and you will get u reduce, which can be represented with the help of z, and your z, so z is this, and this particular thing is nothing but mu reduce, this is mu reduce transpose, and you are multiplied it with the feature space. Okay, feature space x. So this is in the 2 dimension. Okay, you already had seen this is in the 2 dimension, this x. However, this z, this mu reduce is basically in the 1 dimension. Okay, so this is n cross n again, and this is where it is, this is k cross 1. Okay, I hope you understand this pseudocode, and you understand that PCA. If you have any doubt, you can ask me in the comment section. Thank you so much for listening to me.